I want to finish up with the pumping lemma. We talked about it last time, and the way we're thinking about the pumping lemma is that this is dialogue between me and somebody who thinks they have a grammar for a particular language. And if they think they do, then I ask them how many non-terminals in the Chomsky normal form of their grammar, and they tell me, and then I raise that to the power of 2, more or less, and I pick strings longer than that, where I can convince them, guaranteed, that my string in the parse tree that they have to come up with has to have a duplicate non-terminal starting from the bottom moving to the top. And then there's got to be these duplications. So let's do an example of this. We did this last time at the end. We'll do it quickly again. Let's say we're wondering about the language 0 to the n, 1 to the n, 2 to the n over the alphabet 0, 1, and 2. And I want to show you that this is not context-free. So you go home and try to come up with a grammar for it, and you give me the number of non-terminals in your Chomsky normal form grammar, and then I have to come up with a string longer than that, which is in this language. So let's say you tell me that your grammar's got, 5 non-terminals. I raise that to the power of 2, I get 32, and I use strings longer than that, and it's fine. So say I'll use 0 to the 32, 1 to the 32, 2 to the 32. And in general, this number is completely general. I mean, I'd have to call this M or P or something. But you pick the number, I pick the string. Here's my string. Now I give it back to you. And I'm asking you to do the parse tree and tell me things about the parse tree. In particular, the parse tree will divide up this string into 5 parts. The U, V, W, X, and Y. The U and Y represent parts of the tree that are off on the side, outside of the duplication. The V, W, and X represent the piece that comes under the subtree at the top non-terminal of the duplication. And the W part is the part that's derived from the bottom non-terminal of the duplication. So when I substitute the bottom part for the top part and make the parse tree bigger, I get another string that's just like this, except the V's and the X's are doubled. And I can do that again, and then the V's and the X's would be tripled. So the opponent, or you guys, split this string up into 5 pieces. And since I'm forcing you to do it in a particular way, I can guarantee that the middle piece has to be smaller than the n, or the 32. So you get to tell me anything you want about how this parse tree looks, but whatever you tell me, you have to abide by those conditions. And then I have to consider all the possibilities of where this middle section that you're going to give me might be, because you could give me anything. So let's say you told me that the VWX section was all in the zeros, then I'd have to decide what to do. If you tell me the VWX section overlaps the zeros and the ones, I'd have to decide what to do. If it's all in the ones, if it overlaps the ones and twos, or if it's all in the twos. 5 cases. And each case, I would explain why I can still pump out the V and the X and get something that is not in this language. And when I do that, I win. So I'll do that for all the 5 cases. For the case when the VWX is all in the zeros, I pump out the V and X once, and I get extra zeros. So this 0 to the 32 becomes bigger. And these stay the same, and that's not in the language. In the case where it overlaps on the zeros and the ones, there's a couple possibilities. If either the V or X actually contains both zeros and ones, say V was 0, 1, then when I duplicate that, I get 0, 1, 0, 1, and that's not even close to this format. If the V's contain just zeros and the X's contain just ones, then those might get pumped up equally, but they would mismatch the twos. And I can do this for every single case of all the 5 cases. I can pick I equals 2 for my pumping. I just pump it up 1 extra time, that means, and I always win. And therefore, this language is not context-free because it does not satisfy the pumping property that every context-free language is supposed to satisfy. OK. That was review and intro. Questions about that? Let's do another one, and this time you guys are going to be involved. So here's another famous language which is not context-free, WW. The complement of this happens to be context-free. You do that on the assignment that you're working on now, and we talked about it in class. But WW itself is not context-free. That's the set of all strings that are the first half are the same as the second half. All right, so I claim it's not context-free. You claim it is context-free. You go home. You come up with a grammar. You tell me how many non-terminals are in it. I raise it to the power of 2. And I come up with a string to try to make my point. So here's the string I'll start with. I'm going to come up with some bad strings. I have to come up with one string that works. If I come up with one string that works, that I can win the dialogue, then I win. But if I pick a wrong string, you guys will be able to win the dialogue. It doesn't mean that I have no way to win. It just means I made a bad move at the beginning of the game. Right? This is a game. It's back and forth. There exists a string such that any way you split it up, there exists an I that I can pump it. So I have to find the right string. If I pick the wrong one, you might be able to win. I'm going to pick the wrong one now. So here's an example of something in WW. Say your size of your grammar again is 5 symbols, so 2 to the 5th, 32. I just have to pick something bigger than 32, say. Or maybe we should just call the size of your grammar k, and 2 to the k is the length I have to beat. Whatever, and we'll call p equals 2 to the k. So here, p equals 2 to the number of non-terminals that you give me in your Chomsky normal form grammar. That way it's not a particular number. P equals 2 to the number of non-terminals in the Chomsky normal form, so I'm going to pick 0 to the p, 0 to the p. That's definitely of the form WW. It's definitely longer than p symbols. It's twice p symbols. And it's supposed to have this sequence of 5 parts that it can be split into. And I have to see if I can pump that up and show you something that's not WW. So now it's your turn to split this into 5 parts. Pick a good split that kills me. What do you want to let VWX equal?
V be in the one half of the string and X in the other.
OK, so why don't we have, we'll have U equals 0, Y equals 0, W equal 0. So we've got just single zeros there. You should realize W can be empty. U can be empty, and Y can be empty. The only thing that can't be empty in the string is VX together. One of them has to actually exist.
W needs to be either empty or 2 zeros.
Or 2 zeros. Yeah, OK, so let's make it 2 zeros. And now V is going to be, and X is going to be what?
0 to p minus 2.
We got 2 p's here. We got 4 there. Let's add up all these zeros, make sure they work out. P minus 2, that's 2p minus 4. Plus those 4, it's 2p altogether. Why are we doing this? Why are you doing this? Why is Chris doing this? Because now the v and x are the same. And now whatever I try to do to pump them up, the resulting language has the same number of zeros in the first half as it does in the second half. And you guys win. In fact, you can say, I split it like this, and convince me that whatever I choose now, I'm going to lose. Because pumping these up equally makes the same number on both halves of the string. So what does that mean? I got to go back to my drawing board. This string is terrible. I picked the wrong string. I'm never going to show you that this language is not context-free by picking this wrong string. So now let's switch sides.
There's no other way to break it.
Well, there might be a way that breaks it that helps me, but you don't want to do that. You already picked a way that breaks it that kills me. So even if there is another way to do it that's worse, we don't care about that.
We're after the truth here, Sean.
Yeah, but that is the truth. Yeah. No, but all you have to do is find one way that works. If that's the real way the parse tree looks, then I'm just dead. All right, so I got to pick a better string, so we're going to switch sides. Now you guys are going to play my part, and I'm going to play your part. Pick a better string that makes it harder for me to do the splitting. No more 0 to the p, 0 to p. That didn't work. Try something that won't work, please. Want me to do one more that doesn't work, and then you can finally pick the one that does work? How about this? Is this going to be any better? Is that going to be any better? I mean, it's the same kind of string, WW. Now we stuck some 1s in, to make it a little less symmetrical. Where can you split it up to make the v and the x to kill me whatever I try to do?
Equal numbers of zeros on either.
Yeah, you can pick the v to be someplace in this 0 area. You can have it be just a single 0 here, or any number of zeros, and have the x be the same number of zeros in this area. And then when I pump them up, I'm just getting similar amounts of zeros in this section and this section, and it still looks like 0 to the something 1, 0 to that same thing 1. And I can't get anything outside of WW. So you can beat me there too. How can I nail you down so you can't do that? Why are you winning? It's because you can get the V and the X, each of them, to be identical things on the left and the right half of this string. And I can't stop you from doing that. Not with this bad string. How can I stop you from doing that?
Sticks and peas and ones.
Sticks and P's here. How does that stop you from making the V's be, say, 3 zeros here and the X's be 3 zeros there? I mean, Erica's got exactly the right idea. This will help me. It's because the VWX part is supposed to be less than or equal to that number that you gave me originally. That's the constraint. We started from the bottom. We look for the first duplicate. So that VWX middle section has to be relatively short. You can't just say that there's V's that are 2 zeros here and X's that are 2 zeros there, because that would span an area that's too long. It would span over all the P1s plus some extra symbols, and that's bigger than P. So if you're stuck with this condition, then the cases here, I can win every single time. If you pick VWX all in zeros, then I can pump them up and get the first half different than the second half. If you try to straddle them around these zeros and ones, I'll get something like this. 0 to the Q, 1 to the Q after I pump it. 0 to the P, 1 to the P. But now the first half's not the same as the second half. Q is bigger than P. The half is in the middle here. And you can go through every single case. Imagine that you're taking P symbols at the most length and shifting it left to right. It can be all in the zeros. It can be over the border of the 0 ones. It can be in the ones, over the next border, in the zeros, over the next border, in the ones. It's going to be 1, 2, 3, 4, 5, 6, 7 cases. All the arguments are similar for each of these cases. It makes the half and half lopsided. But they're all the same kind of argument. I can pump it up with one extra pump, I equals 2. So that's a good idea, putting those P's in there. And you'll notice that this is a very big deal. Without this constraint, I can't win the game. And that's why we go from the bottom to the top in doing that pumping lemma proof, so I can guarantee that that constraint actually is there. Well, let's try a language that I won't tell you whether it's context-free or not. We'll try to prove whether it's context-free with a pumping lemma. And if we don't get anywhere, maybe we'll conclude that the pumping lemma actually, that the pumping property actually holds for that language. Maybe that'll make us think that it is context-free. Let's try. You shouldn't be able to win the game if the language really is context-free. Right? The pumping property works then. So the contrarian trying to show you that the pumping property doesn't work, they shouldn't be able to succeed if you start with a context-free language. The only reason I won here is because we started with a non-context-free language. So let's pick a language maybe that is context-free and show that I can't win no matter what I try to do. Maybe that'll make this idea a little more clear. All right, so somebody pick their favorite context-free language, or should I pick one? Who wants to pick one? It's got to be your favorite. It can't just be any context-free language. Palindromes are your favorites?
Sure.
All right. Are there 2 L's in palindromes? Why? All right, let's do palindromes. So somebody in the class doesn't believe that palindromes are context-free, and they want to convince you that they are not context-free. And that person is me. All right? And I don't care that you showed me a grammar or a machine. I still say they're not context-free, and I'm going to prove it to you with the pumping lemma. And I'm not going to be able to win this game unless you guys make a mistake. So you shouldn't make a mistake. You have to do your part well. OK, so you say you have a grammar that accepts palindromes. And I say, how many non-terminals does it have? You actually do have a grammar this time. So how many non-terminals does it have? Yeah? Can you do it with less? Chomsky normal form. We don't. Yeah, let's say 5 or 6, whatever. All right, so I pick strings that are bigger than 2 to the 5th or 2 to the 6th. Let's call that strings bigger than size p. And I'm going to give you this string. 0 to the p, 1 to the p, 0, 1 to the p, 0 to the p. Okay, there's a palindrome. And now you split it into 5 parts, and then I'm going to win. Well, I won't be able to win if you split it into a good 5 parts. How can you split this into 5 parts, identify the v and the x for me, such that no matter what I try to do with the pumping, it always still ends up as a palindrome? In other words, I can't convince you that your grammar accepts anything except palindromes. Where should the v and x be? Where should they be? You can make the v some number of ones here, and the x some number of ones here, the same number. And fiddle with the w and the u and y any way you want to get the rest of the symbols. Then whenever I pump it, I'm just going to get 0 to the p, 1 to the q, 0, 1 to the q, 0 to the p. Just more ones on each side, equal numbers. And it's still a palindrome, and I'm dead. So I'm going back to the drawing board. Okay, I'm not going to let you do that this time. I'm going to make the 0 to the p this time. Remember, that was Erica's trick last time, so I'm using Erica's trick again. So now tell me where the v and x are. Now I think I'm going to win. They could just be in the middle here, right? No matter what I do, no matter what string I pick, every single string I pick, every single one, can be divided into 5 parts so that VWX is smaller than the p, so that whatever I pump it up, and any I up to infinity, it will always end up being a palindrome. That's what the pumping lemma says. And it's true because of the structure of this grammar. I'll never win this. So that's a good way for you to see whether you have one. If I picked something that wasn't context-free, you should be able to win in this long argument. It's somewhere along the way in the adversarial back and forth. And the way you should write it out is as formal as you feel comfortable with. It can be just a page of English explaining the dialogue and how you convince the other person that when you finally pump it up, you get something not in their language, no matter what they do. And if there's many cases involved, then divide it into those cases and carefully enumerate them. And if all the ideas are the same in all the cases, just say, okay, this is the same as the case before. You can see that. You can shorthand what you're doing, but make sure it's nice and clear. All right, are there questions about this? How about this? Last one. We did this with regular sets. Just numbers of zeros that have a square value. So 0, 0 to the 4th, 0 to the 9th, 0 to the 16th. Is that set context-free or not? It wasn't regular, and now I wonder whether it's context-free. What do you think? You think no? Or if we think no, then we've got a proof to do. So let's try to do this with the pumping lemma. If we fail with the pumping lemma, maybe we'll be more convinced that it is context-free and go back to the drawing board and try to do a grammar. And that's a good thing about these kind of things. You never actually fail, because when you fail on one side, you go back and work on the other side. Or maybe yet, if you're a pessimist, you're failing twice. But I like to think of it that you always got something else to try. Okay, so 0 to the x squared. Somebody picks the number of non-terminals in the alleged grammar. We raise it to the power of 2. They tell me that value. That value is p. I have to pick something that's bigger than p symbols, that's in this language. And since I got no better idea, and I have no idea if this is going to work or not, I'll just do the obvious, 0 to the p squared. That's got way more than p symbols. It's in the language. Now you split it into 5 parts, such that the VWX part is less than or equal to p symbols. Well, there's only one symbol in this alphabet, just 0. So basically, you're going to tell me how big that middle part is. How many zeros are on the v part? How many zeros are on the x part? And the total of the v's and the x zeros altogether is going to be, at most p. Okay? Well, I'm going to have to handle any number you give me, from 1 all the way up to p. And whatever number you give me, I'm going to show you that I'm going to pump it up one time and it won't be a square. Okay? Right now, UVWXY is 0 to the p squared. What's the range of new strings that would come about from you picking the Vx anywhere from 1 all the way up to p? If you picked it 1 and I pumped it up once, then my new string would be 0 to the p squared plus 1. If you picked p, that's the biggest you could pick the v's and the x's. You could have w be empty, and the v and x together includes all the symbols. Then the biggest it could be is 0 to the p squared, pump it up once, plus an extra p. So if I pump it up once, my new string is going to be 1 bigger than this square at least, and at most, p bigger than this square. So it definitely can't be this square because it's bigger. And the next square is p squared plus 2p plus 1. That's p plus 1 squared. And it doesn't make it that high. This is actually the exact same idea that we did in regular sets. There's nothing different about the idea. With a single 0, the v's and the x's just get bunched together because they don't make any distinction whether they were in one group or two groups. And the argument works the same as we did before. So it's true that I can win this, and that square is numbers of zeros is not context-free. And neither are primes, and neither are anything that really takes any computation. You need a Turing machine to get all those things. So I think on one of the homeworks, we tried to do one of these 0 to a composite number. Let's try to do this just very quickly. All right, you come up with that p again, and then you give it to me. And I need to come up with something which is longer than p and definitely a composite number. So I'll come up with, how about 0 to the 2p. That's a composite number, and it's bigger than p symbols. You have to split this into 5 parts. And tell me what this middle part is. It's going to be between 1 and p symbols, somewhere in between. And then I have to pump this up and show you somehow that I definitely get a prime number, not a composite number. That's how I'm going to win, to show you that I don't get a composite number. Can I win this? What's a good UVX, VWX for you guys to pick? What if you pick the v and x together to just have 2 zeros in them? Say, make the v a 0 and the x a 0. Then whatever I do to pump up these v's and x's, I'm getting multiples of 2 added to this string. And 2p plus any multiple of 2 is still going to be an even number, and it's composite. I'm never going to get a prime number. Now, maybe I should go back and pick a better string. But anything I pick here, 3p, 8p, you're just going to pick the v and x to be 8. I'm just going to be, in fact, you could pick it to be p. Right? If you pick it to be p, then I'm getting multiples of p added to some multiples of p, and I don't get anything either. Now I could do something weird. What if I did 2p plus 3? You know, then you can't do that trick on me. But how do you know that 2p plus 3 is even a composite number? It might not be. I got to guarantee that that's a composite number. So if I do it by keeping this, you know, some multiple of p, then you can always win. So what does this say? This means you guys won, at least so far. I can't get a better string. And in fact, I don't think I can get a better string. I think you can always win. That means that 0 to the composite satisfies the pumping property. It doesn't mean necessarily that it's context-free. It happens to satisfy the pumping property, but it turns out it's not context-free. The only way to really show that this is not context-free is to look at its complement, 0 to the prime. Here I can win. You can go through the details. I won't do it with you now. Here I can win. If you guys pick Vx, I can pump it up enough to get a composite number. I have enough control to win this one and show you that this is not context-free by the pumping lemma. And then since context-free languages, are they closed under complement? No, right? Too bad, huh? Wouldn't it be nice if they were? Then I could say that 0 to the composite is not context-free. So what do I do now? Maybe 0 to the composite is context-free. Maybe this is like the WW. Right? This is WW complement, and that's the WW. Sorry, that's a WW, that's a WW complement. How do you know about 0 to the composite? What is closed under complement?
Regular.
Regular sets are closed under complement, right?
Yeah.
Deterministic context-free languages are closed under complement. Can we use that to figure out that this is not context-free? We can use it to figure out that that's not deterministic context-free. Right? But that's about all we can do right now. So you have to be careful with these kind of closure properties to remember what's closed and what isn't, and to use the pumping lemma when you think it's going to work, but be aware that it doesn't always work. And it's not always the end-all of showing something is not context-free. When there's a single non-terminal on the left, it's called context-free because imagine when you're doing a derivation. A goes to BCA, and now I can do C goes to AA. So BAAA. This is a non-context-free derivation because it says you can substitute AA for C, but only in the context if it appears after a B. Otherwise, you can't do it. So context-free means make any substitution you want. I don't care what context this non-terminal appears in your sentential form. And these kind of things say you can make the substitutions, but only in the context of certain symbols around them. And this gives you tremendous power to make it feel like a machine. And this gives you less power.
And the more general ones are called what?
Use the term context sensitive.
Yeah. There's a hierarchy in between. There's unrestricted grammars, which are the same as Turing machines. And in between them, there's a category called context-sensitive grammars. Things that have bigger symbols, more symbols on the left, are called context-sensitive grammars, but they have a particular constraint that still exists, and that is that the number of non-terminals here has to be at least as big as the number of non-terminals here. You can't have things do this in a context-sensitive grammar. In an unrestricted grammar, you can do this also. And context-sensitive grammars are not exactly the same as Turing machines. They're a subset. They're basically what you can do in order and space, algorithms that take order and space. But we're not distinguishing between those categories because it gets a little too abstract. So we're just thinking of regular grammars, context-free grammars, and unrestricted grammars. So after this, it's just anything you want from the point of view of this class. That's a good question. Other questions before we go on?
Yeah, as long as you're defining terms, what does LRK stand for?
Oh, that's a big question. The L stands for left to right. And well, I guess the real answer is I don't know, but I'll tell you what it means. There's LLK and there's LRK. And they both parse from left to right, but this parses top down and this parses bottom up. So I'll say that the R stands for bottom up. I don't remember what the actual abbreviations stand for, but this is a top-down parser that goes left to right. This is a bottom-up parser that goes left to right. And the K means that they need to look at the next K symbols in order to be able to do their deterministic parsing. They both correspond to deterministic pushdown machines, but the K means that they're looking ahead a few symbols. Our normal deterministic pushdown machine doesn't look ahead symbols at all. It looks at the next symbol, decides what to do. Looking ahead means it can actually see a few symbols ahead to decide what to do to help it. So, well, now that you mention this, let me say a few more words because it will affect one of the problems in your homework at least. On your homework, I asked you to do this language, equal zeros and ones. Okay, not 0 to the n, 1 to the n, but just an equal number of zeros and ones in the string. Who has an idea about how to make a push-down machine that does that? How would you do it? Give me a plan. Give me a man, a plan, a canal.
You can,
Yeah, Chris, go ahead.
well, you can have a stack that keeps track of your surfeits and deficits, and you can randomly throw zeros and ones in and move your stack up and down accordingly, but you can only quit when your stack's empty.
Okay, so the stack goes up when you see a 0 and goes down when you see a 1. What if it gets empty?
Then fill it up with one surfeit symbols.
Okay, what if it gets empty and the next symbol is a 0?
Well, then you throw in a zero surfeit.
Okay, so when it's empty, I have to look at the next symbol, and if it's 0, then I go into a place where I push zeros on, and then when I see 1s, I pop them. And if it's 1s, I push 1s on. When I see zeros, I pop them. If it gets empty again, I can start again. And then I accept whenever I get to the end of the string and the stack is empty. That's completely reasonable. And on the homework, I asked you to do this deterministically. How do you do this deterministically? Let's take your strategy and kind of write it up. At some point, there's going to be a state, and on this state, if you see a 0 and there's a 1 on the stack, then you pop it, right?
Yeah.
And then at some point, you see empty stack, empty, and you accept, right? Something like that. What else do you have here? What happens if you see an empty stack here? And there's a 0 on the 0, empty stack. What do? You're going to push the 0, right? Look at these two choices. How do you know which one of these to take? In other words, what if I'm reading through the string and the zeros and ones equalize after some amount of symbols?
Then we need to have something coming out of the accept state. Instead of having to just fall off the end if there are more symbols. If we find more symbols in our string,
We just go back into the game.
Yeah, but it's already non-deterministic.
But it's non-deterministic,
What is it?
right? Because at this point, I don't know whether to stop and say I'm done. And in fact, let's say they equaled out after 3/4 of the way through the string. Couldn't I just not read another symbol and say I accept? Well, I guess then you would die. That's no good. And if you want to come back, you can come back and fix it. But at this point, you have a choice. Do I continue looking at symbols, or do I stop and accept? And there's no way to know if the string is over yet, unless you look ahead at the next string. So technically, there's no way to do this deterministically. Technically, you're really stuck with non-determinism here, even though you should got a gut instinct that this isn't particularly non-deterministic. I just can't look at the next symbol, and I'd like to see if I'm done yet. So my solution, the actual solution to this is very technical and annoying, and it has to do with these LRK grammars. This is not an LR0 grammar. An LR0 means you don't have to look ahead at all. This is an LR1 grammar. It's deterministic, but you got to be able to look one symbol ahead to see if you're really done. Right? So you get one little extra look ahead. I want to look ahead to see if there's something there. If there's something there, I know to do this. And if there's nothing there at the end, if it's really empty, I'll go do this. Then it's no longer non-deterministic, but I need to look a symbol ahead to make it deterministic. That's the distinction between LR0 and LR1. This is an LR1 grammar, but not an LR0 language. So you asked the question, you opened up Pandora's box. The way that I tell people to handle this, because usually we don't spend 3 or 4 lectures talking about LRK grammars, as interesting and as difficult as they are, we don't spend time on it. So what I tell people to do is, in these situations, you can always assume that at the end of your string is a special symbol, like a pound sign. Right? And that will end every input string. And that way, instead of the E here, you have a pound sign. And now it's deterministic again. And what this basically does is take away the whole issue of having to deal with deterministic things that seem like they have to be non-deterministic, but really they're deterministic, and let's make a whole theory about how to show they're still deterministic. Let's just chuck a symbol on the end and not deal with it. Right? So if you ever have this difficulty and you think you can do a deterministic one, and the only thing that's in your way is looking at the end, then imagine there's a special symbol at the end. I mentioned this once at the very beginning when we talked about grammars, and it's coming up here. So you can do this if it makes it convenient for you. That's the upshot.
So if you want to know the end of a string, you really have to you don't need to look at grammar to know just that the string is ending.
Right, right. And there's a theorem that says that LR0 grammars are the same as the deterministic context-free grammars, context-free languages that have the prefix property. In other words, if you put a special symbol on the end, there's no prefix that could possibly be part of that language. So if you take any language that's deterministic and put something on the end of it, those are the LR0 grammars. In other words, if I put this pound sign here, then I can get all the LR0 grammars. If you get this, fine, and I don't see how you really could with just a brief explanation like this, but you get a little flavor of what these LRK grammars are like. We're still hoping to spend some time on this in recitations. It'll be an advanced topic, and it won't be part of the main course, but hopefully we'll get time to do it. All right, so...
Just in that
Yeah.
machine there, if
Yeah.
you start with a 1, and the stack is empty, what happens?
All right, we'd also push the 1 on, I guess.
Push the 1 out,
Yeah.
and then
So if there's 1s on the stack, we might need two different states here. If you start with a 1, go to a state that pushes 1s and pops 0s. If you start with a 0, yeah. Yeah, I didn't write the whole machine down. But you're right, Neil. It needs a little bit of thought. Yeah. We did this 2 months ago. Or 3 months ago. We did this in algorithms when we talked about dynamic programming. And I know what you're thinking, oh gee, but I don't remember that. Don't build on what we did then. I'm not. I'm going to do it from scratch. I'm going to pretend you never saw it. And I'm going to pretend that if you did see it, you never understood it. And that if you thought you did understand it, that you were wrong and you really didn't understand it. All right. Now everybody's got to be willing to listen. Now that we're on the right path. This is an algorithm named for the 3 people that worked on it independently. Koch, Younger, and Cassimi, I think are their names. And they came up with an algorithm for parsing that takes a context-free grammar, takes a string, tells you whether that string can be generated by the context-free grammar. Their algorithm runs in order n cubed time. And that's a very important result because it takes it out of the exponential time algorithm that we got from Chomsky normal form. Chomsky normal form, remember, has 2n minus 1 production steps to get a string. So 2 to the 2 to the n minus 1 is the size of the trees. And that's the worst case for finding whether a string is generated or not. Just generate all the trees. We want to do better than 2 to the 2n minus 1 of Chomsky normal form brute force method. And this is a lot better. This is polynomial. And the idea of this is dynamic programming. We think of kind of a recursive idea and notice that the subproblems are being computed many, many times. Keep track of each subproblem once, and we'll get the answer to whether a given string is generated by a given grammar. It's a dynamic programming style algorithm. Dynamic programming. And I'm going to show you all the details about this and do a particular example. But before I do, I want to just mention that this is not used practically for any kind of parsing nowadays, because there are better polynomial time algorithms than this. What's more, this algorithm works for any context-free grammar. It doesn't have to be LRK. It doesn't have to be deterministic. Any real grammars that work for programming languages are LRK grammars or LLK grammars. They are deterministic. And therefore, you can probably implement them more quickly and more easily. This is just completely general and shows you that it is possible to do parsing even for non-deterministic machines in polynomial time. The real fast algorithms that work with LRK parsers are linear time, and in practice even, in real time, maybe faster by a constant factor. I mean, very, very quick. They basically compile your code by looking at it in one pass. All right. So with all that as intro, let's go ahead and write an example grammar up, and I'll show you how we're going to go ahead and make a table and figure out whether this grammar generates a given string. Here's the example grammar. Again, as the last few examples we've had, it's very useful to have this in Chomsky normal form. It makes the description of the algorithm very concise and without a lot of exceptions. So there's the grammar. And here's our candidate string. I'll put it up here. 1, 1, 0, 1, 0, 0. Okay, questions so far? We're going to try to answer the question whether this string can be generated by this grammar. And if you want to fiddle around with the grammar and just kind of brute force or play with it, you can try to figure it out yourself. And then I'll show you how the machine is going to do it. Are there questions? Ready to go on? The basic idea is that we're going to try to figure out, for each of these non-terminals, what substrings of this string they can generate. For example, let's say I knew that B could generate 110, and I knew that C could generate 100. Then for sure I would know that A can generate this whole string, because A generates BC, and B generates the first half, and C generates the second half. If I know what small pieces of this string are generated by the other non-terminals, I can look at A and see, if I put those two together, whether I get my whole string. So let's say I know that B generates the single string 1, and C generates these 5. Same thing. I can get that A generates the whole string. There's a lot of places to split this string up. I can split it 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. So we're going to somehow try to build up all the different substrings of this string and which non-terminals can generate them. And then build those up in terms of each other, recursively, until we find out which non-terminals can generate the whole string. And if the start symbol is among those, then we say yes. And if the start symbol is not among those, we say no. In this case, A is the start symbol. Okay, questions so far? So I need one notation, and then we'll do some details. Here's the notation we'll use. We'll call this Vij. This is going to be all the non-terminals that can generate a certain piece of this string. I'll tell you what piece in a second. All the non-terminals that generate J symbols of this string, J symbols of your string, starting from symbol I. Okay, we need that notation because this is going to give us a way to identify every single piece of this string and which non-terminals can generate it. For example, let's do a particular example. Let's do V41. V41 are all the non-terminals that can generate one symbol starting at position 4 of this string. 1, 2, 3, 4. That means the single string 1. Which non-terminals can generate the single string 1? A and C. Why is that so easy? Because Chomsky normal form is the nicest, simplest form in the world. You just look it up, and there they are. If it generates a single 1, it's got to be there in a production. So this equals the set A and C. How about V31? What does V31 refer to? Again, one symbol starting in the 3rd position. And what generates that? B and C. Okie doke. Who thinks they get that notation? Right. This is the base case. These are the ones that you can just look at and figure out yourself. When J gets bigger, it's going to be harder. And it's going to be based on smaller cases that we've already computed. And we're going to do this in a bottom-up dynamic programming style, because if we did it just recursively, we would compute the same base cases many, many, many times, and that's where the exponentiation would occur. We want to avoid that. So we're going to do these once from the bottom up, store them, and work our way upward from the bottom toward the ideal. What's the ideal? And then I'll answer your question in a second, Joe. I saw your hand. What we really want to find out is V15. I mean 6. V16. We want to find out which non-terminals generate 6 symbols of this string starting in position 1. That will give me the answer I'm looking for. And V16 hopefully will be based on these smaller cases. All right, Joe, you had a question?
You just count from the left or from the right? Or
You mean for the I symbol? When I say I'm starting from the second symbol?
Yeah.
From the left. So V41 is 1, 2, 3, 4, and then 1 symbol from here, meaning just that 1. V15 means 1, and 5 symbols to the right. 1, 2, 3, 4, 5. Okay? All right. Let's make a big table. V. Here's J, here's I. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's fill in the base case as we know it and work our way to higher cases. The cases will work from left to right. J equals 1 will be the first base case because those are substrings of length 1, all the way up to substrings of length 6. We're going to work this way. It doesn't matter how we do it up and down, so we can start any place. All right, so V of 1, 1. That means what are all the non-terminals that can generate 1 symbol starting in the first position? What are they? That's the symbol 1. AC. Agreed? What about 2, 1? That's the next single symbol string over to the right. That's another 1. All right. What about the next one? Who can do the next one? Neil, you got this stuff? Is it making sense? Right, BC, because it's a single 0. Next one is a 1, right? So it's AC again, and then there's 2 more zeros, so 2 BCs. Okay. All right. Now we move over to the next column. And now we have to think a little bit, because this was just the base case, and the next column is going to have to be something that is dependent on the first column. And we'll do the same thing. We'll go down in order. But now we're only going to go this far. Why don't we go up to here? Right, 6, 2 means you go off the end of the string. There's no 2 symbols past the 6th one. So this table gets filled up only about halfway. The diagonal is going to go up this way. All right, so what does 1, 2 depend on? Let's look at it. 1, 2 means what are the non-terminals that generate these 2 symbols? Starting in the first spot, 2 symbols over. It depends. Let's write this down. I want to make sure you get this, even though you can eyeball it and tell me, but I want you to think about it. It depends on 2 other values of V. The left side of this and the right side. This one is V11, and this one is V21. It depends on V11 and V21. Let's look at V11 and V21. They're here and here. And let's ask ourselves, is there any way to combine these with this one on the left and this one on the right and get productions? Well, there is. You can have AA, AC, CA, or CC. Those are the only ways to connect V11 and V21. Now let's look at our production lists and see if AA, CA, AC, or CC shows up anywhere. AA is there. What goes to AA? B. So B goes in this list. CA, is that there? No. AC, is that there? And CC, is that there? No. So the only way you can generate a 1, 1 is through a B by generating an AA, and therefore A can generate 1, A can generate 1. Putting them together, B can generate 1, 1. So at this level, at the second column, the value here depends on two values from the previous column. The value here is going to also depend on two values from the previous column. Every one of these is going to depend on two values from the previous column. What two values does this one depend on? This is 2, 2. 2, 2 looks like this. It depends on this one, which is called 2, 1, and this one, which is called 3, 1. Here the combinations are AB, CB, AC, and CC. Do any of those show up in any of our productions? AC does?
AB and CB.
AB and CB. And they give us what non-terminals go to those productions? A and C. How about here? BA, BC, CC, CA. How do you get A? Because it's BC. Can you get B? No. Can you get C? No. So just A. Next. I think we've did this.
This is just going to be full of non-terminals.
Actually, you can have empty sets here. It's possible that none of these will combine to get anything, and then you put the empty set in.
But no two non-terminals together, not BC.
No, just single sets of non-terminals, absolutely. So this is the same as what we did here. So this is going to be AC. And we haven't done this yet, BC, BC. Is there a BB? I don't think so. A BC? Yes, that goes to A. CB goes to C. AC. Okay. If you understand this so far, you're 95% of the way there. Right? It gets a little bit more involved in the next few columns, but not too bad. Are there questions so far? Yeah, Joe, you have a question? You concentrating? All right, let's go over to this one, V13. Now, unfortunately, but necessarily, we need to do a little more in this column. V13 cannot be constructed by just figuring out which non-terminals construct the left symbol and which non-terminals construct the right symbol, like we did in the second column, because now we have three symbols. So now we actually have two ways to split these three symbols up into two parts. One is that we have a single 1 followed by a 1, 0. The other is that we have a double 1 followed by a 0. Let's identify both those pairs. The single 1 is V11, and the 1, 0 is V22. A double 1 is V12, and the single 0 is V31. We have to do the same thing we did before, but we have to consider this combination and this combination. Because any of those combined together would be able to give us 1, 1, 0. And now you can see where the exponentiation would come in if we would actually call these recursively. You get a lot of these things showing up again and again. V12 was just called before. Now we're calling it again now. We didn't want to call it and call it and call it and call itself over and over again. That's why we're working bottom up. Now let's look at these pairs, V11 and V22. That is this one and this one. And what's the next one? V1, 2, and 3, 1. So it goes here and here. Okay, the first one, see the beginning of my arrows? Did I do this right? V1, I wrote it wrong. V1, 1 and V, no, it's okay. V1, 1 and V2, 2. And then afterwards, V1, 2 and V3, 1. Start here, that's your first pair. Go to the right and go down to the left in the diagonal to get your next pair. Right? Let's look at the first pair, AC and AC. This gets a little tedious, but if you look, actually we did that before, so I know you get a B. Right? Now we're going to do B and BC, which gives you no, I don't. B, B, and BC. So
You can get a CB.
you can't get a CB. You just get just BC. You just get A, right? Right. BB doesn't appear. BC does appear after the A, so A gets put up there. Let me stop for a second. Questions about this? So we have two pairs to look at. Following this geometry, I'm going to erase this arrow for a second. If you're over here and you want to know which two pairs to look at, you can go back to the drawing board and figure it out like I did there explicitly, or you can use the geometry to help you. Start over here to the left of the empty square you're working with. That'll be the first element of your pair. Start down here diagonally, move downward, and move to the right. So that's the first pair, and that's the second pair. Let's check if that works. This would be 2, 1 and 3, 2. 2, 1 is the single symbol 1, and 3, 2 are the next two symbols over. They give you 1, 0, 1. And that's exactly what we're trying to get here. We're getting 2, 3, which is 1, 0, 1. So to figure out whether 1, 0, 1 can be accepted and by what, you go ahead and you split it into this pair and then this pair. And this is going to work all the way down. So let's actually do these. Let's finish this whole example. We're over here. Here's the first pair we do. We get AA and CA. What do we get from that? It's the B. And now we get a AC, which gives you just B. And we're not going to add B twice. It's a set here. So that's all we get is B. Let's go down to this one. Try to do it in your head. You start from the left and then go down diagonally to the left. So this one and this one are the first two you look at. BC and AC. What do you get from that? And I think you get something else. No, just A. You're right. Just A. And now we move to the right here and move down the diagonal here. You get AB, AC. And that's A. So just A. Finally, this one, go to the left, go down diagonally. That's the first pair. You're going to work this way and work that way. AC, AC gives you B. AC, BC gives you, I think, A and C. Okay, so little by little we are learning which non-terminals can generate which pieces of this string. Let's look at a particular example. This is 4, 3. That means starting from the fourth spot, 1, 2, 3, 4. The last three symbols, mainly 1, 0, 0. What non-terminals can generate 1, 0, 0? All of them can. You can start with any one of these non-terminals, and they will all generate 1, 0, 0. So that's what we learned so far. There's more work as we go to the right, but fewer entries. So it won't be too bad to finish this up. And that's the answer we really want. All right, questions so far before we move on? And I want to do the next one explicitly and then show you the geometry just to make sure everybody gets it. And after I do that, we'll finish the table. So the next box we're going to do is V14. Okay. Sharon, you getting this? Is it making sense? Here or there? All right, let's look at V14. Do you know which part of the string V14 is referring to?
It's 1101.
Good. Starting at the first symbol, 4 symbols down. Good. Now we want to figure out what non-terminals generate this substring. And that can be done by looking at their productions and figuring out whether the left production generates part of the string on the left and the right production generates part of the string on the right. So there's a lot of ways to split this string up. You can split it 1 and then 3, 2 and 2, and then 3 and 1. All right, so do you want to try to give me the pairs of boxes we have to look at to determine which non-terminals generate each part of those pairs?
So it could be 1, 1, and then down. And the 101, so that would be 3, 3, 2.
2, 3. The number of symbols comes second. Where you start comes first. Good. What's the next one? Or maybe somebody else. I think you got it. No volunteers?
1, 2, and 3, 2.
1, 2, and 3, 2. Is Erica right? Is she always right? Mm-hmm. Next one. One, 3, 4, 1. 1, 3, 4, 1. Is that it? I think that's it, right? Okay. I could actually, maybe at the very end, I'll write the triple loop that generates these indices to get this going. You could do it if I forced you to, but it's just ugly. I mean, and it's more of an algorithms thing. You can write this with 4 or 5 lines of code and get the I, J's, and K's all working out here. I mean, it's not too bad. You notice this first one stays the same. This increases by 1 each time, the 2, 3, 4. And the sum of the second indices always equals 4. 1, 3, 2, 2, 3, 1. This is a very nice, pretty straightforward pattern there. It isn't too tough to write the code to get those indices to generate, based on the original indices 1 and 4. The second 2 add up to the 4, and, well, you get the idea. Let's go back here. Geometrically, this works exactly the same way it did before. Left to right in the column, in the row that we're looking at, and then down left in the diagonal. If better, 1, 1, and 2, 3. Is that right? Okay, so let's look at this. A, B, A, C. You guys think, and I will fill in. Computer science by democracy. C? A, B, C, B gives you C?
Also,
AC. Okay. Let's go on. BA. Nothing? BA with AC. How do you short circuit this a little bit? We already have AC here, right? The only thing we could possibly add on is B. The only thing B possibly goes to is AA. So let's see if this and this give you AA. Oh, they do. So, look, there isn't that much value in learning how to do this quickly because a machine can do this. But as long as we're doing this example to understand the idea, that is the important point. Let's at least try to get through the example painlessly without cluttering up your brains too much. It's the idea that's important, not this particular skill of going through it quickly. All right, next blank spot. Left, down. So AC and A. AC, AC. B? And then B and BC. Go down to this one. BC and BAC. It's a lot. All of them? If there's all of them, I don't have to keep going.
You can't get B, can you?
Yeah, you can get, oh, there's no A there. No, you can't get B.
I can't get B. All right, so we'll have to go on before we include B. So we did these two, and now we're going to do this one and this one, and AA, that gives you B. All right. Well, now we're up here. Without going back to the drawing board, it's the same geometry this way, down the diagonal. So ACBA. All three? That was easy. Now we don't have to keep going this way and that way because we got them all already. Let's go here. Left, down, AC, ABC, same thing. Yes, ABC. And now we're way over here. So this means that every 5-length substring of this can be generated by every one of those non-terminals. And now we're up to the 6th one. This means can we generate the whole string? This depends on whether AC, ABC can be done, and I think that should give you everything. So we stop there. We look, we see that A is there. Therefore, this definitely generates this string. Now, a couple things while you ponder this example. In the algorithms class, you had an assignment question, I'm pretty sure, because it's the kind of question I would have put in. I didn't go back and check, but it's what I like you to try to do, to put more information in this table. So when you're all done, you can backtrack and figure out not just whether the answer is yes or no, but actually which production to use. Did I give you that question? Yes. All right. It's not completely simple to do that, but it's also not terribly hard. And it's not something I want to talk about now, because you've seen it once before. It can be done, and it's not particularly part of theory of computation. It's more an algorithms issue. But the point is, this algorithm is not just going to answer yes or no. It doesn't take too much extra effort to add in information along the way so that you can backtrack and actually figure out how to parse it, to come up with the actual parse tree. And how long does this algorithm take? That's the next thing. Well, we have a bunch of squares that are about n squared over 2, where n is the length of our string. And how much does it take to fill in each square? Well, the base case takes 1 step, more or less. But every time we move to the right, it takes 2 steps and 3 steps and 4 steps and 5 steps and 6 steps. So this is like you have n squared things, and each time through, you're summing up a little bigger piece. We actually did this sum. We did it in discrete math. We did it again in algorithms. I'm not going to do it again now. But if you add up this sum, it ends up being a constant factor times n cubed, like 1/3 n cubed. It's definitely less than n cubed, but it's order n cubed. The worst case is here, where you're really doing n operations. But it doesn't add up to order n squared. It adds up to order n cubed. It's very similar to the sum of the first n squares. 1 squared, 2 squared, 3 squared, 4 squared. It's a little like that sum. And it ends up being n cubed. So this algorithm runs in order n cubed. Practically, it's a very small constant factor in front of the n cubed. So you could probably actually run this on some very small programming languages and grammars and make it work and not have it be too bad. And it would do parsing of any context-free language, any context-free grammar. That's a loaded question. I get this horrible feeling we made a mistake. Why doesn't 2-4
Not much of a mistake.
get us? It wouldn't matter, right? But why doesn't 2-4 get a C? Let's look at 2-4 again. 2-4 combine AC and B, AB and CB. I guess CB already there. It should have gotten. This should have a C in it.
To make it fit.
But since everything else has everything already, we don't have to change everything after that. But you're right. That's just a mistake.
Where did that come from? 1, 1, and 2, 3.
AC, oh. It didn't come from that pair, right? And it didn't come from this pair. Uh-oh. No, I don't think it needs it.
Isn't it 1, 1, 2?
Somebody else say it does need it. I'll put it in again. Let's check again. We go to the left here, AC, and we go down diagonally. So AACA. We're going to have to get CB, and I don't see CB. No, so it is okay as it stands. Where did you think we could get it?
1, 1, and 2, 3.
1, 1. Oh, but we're not going up there. For this guy, we just go straight left.
Oh, I'm sorry.
1, 1, and 2, 3 would not generate
Oh, yeah.
2, 4. Right, okay. So we're okay.
Oh, racist on my word.
Right.
And the thing that we were doing humanly, not going on when all we needed was a B, would that be any economy in our program?
I don't know. That's really an engineering kind of question because you don't want to spend too much time just checking for that either, right? It wouldn't take too much of a check to see whether you've gotten them all. But I think in big grammars, you don't usually get them all. I don't know. I mean, I better not guess. I don't know. I haven't done experiments to see whether this parsing algorithm would speed up in real time, noticeably if you put those extra checks in. But at the same time, nobody does because nobody uses this. I mean, there's these better linear time algorithms, so I don't think anybody's spending any time trying to optimize the CYK algorithm.
You can do it in linear time?
Yes, you can do parsing in linear time. Only with these LRK grammars, not in this general case. But nobody works with grammars in the general case. But with LRK grammars, you can definitely get it down to linear time. There's a very nice paper that first describes, I think, the first linear time algorithm. Actually, it might be n squared. I don't know if it was linear time in the first version of this paper. But I think in 1970, there's an algorithm by a guy named Early. I think that's how you spell his name, either with an E at the end or not, I'm not sure. Early's algorithm, which describes a parsing that takes linear time for deterministic context-free languages. And it's in the Communications of the ACM in 1970. It's reprinted. There's one Communications of the ACM, I think around 1980 or 1990 at the turn of the decade, which prints like all the greatest hits of the ACM papers, including like, the Unix operating system, Ethernet, Early's parsing algorithm, Codd's paper on relational databases, all like the seminal papers. And that's one of them, and you can look it up. It was reprinted.
Is there a way to look at a grammar like that and say whether or not it's deterministic or not deterministic? Like you can look at the machine and it's very obvious.
There's no obvious way. You can take a grammar and check whether the grammar is LRK, but it's a complicated definition. The reason I haven't told you what LRK grammars look like is because I have to define something called the first and then the follow and give you a condition about the first and the follow sets. And it takes a whole lecture just to understand the definitions, and it's not a fast thing to check. You get a whole homework assignment just to get used to it, but you're definitely not an eyeball kind of a thing. But more importantly, if I give you just the grammar, the question is about the grammar. I could give you a stupid grammar, and there might be another LRK grammar that does the same language, even though this grammar I gave you isn't LRK. So the question is just about the grammar, not about the language.
Right, but in terms of whether or not you could use a better algorithm, how do you know, given a grammar, whether or not you have to use something that is
There's a very, very specific way of checking if a grammar is LRK, but it's complicated. It's quite complicated. And the complication has to do specifically because it's got to be something which parses deterministically. So to check whether that's true is an involved process, but completely mechanical, and you write a program to do it. That's exactly what Dimitri will do if he gets to it. He'll show you exactly how to determine if a grammar is LRK, and you end up, it's very interesting, you end up creating a non-deterministic finite state machine of legal items, and then a deterministic finite state machine of parsing tidbits. It's very neat, but it's complicated. Questions? All right, let's do a little more before we quit, and then we'll quit today. Questions more about this? Okay about this? There's really just one more topic to this ring in our bullseye of hierarchy for context-free languages, and it's the discussion of closure properties and decision algorithms for context-free languages. This also gives a nice segue into talking about the next level of the hierarchy, Turing machines, because Turing machines, one of the main topics we talk about with Turing machines is decidability and the existence of problems that are undecidable, problems that are often very, very practical. Closure is not just connected with decision algorithms. If things are closed and you can minimize them, like with finite state machines, you can almost decide anything. So there's a close connection between closure and decision algorithms, but closure also has to do with showing things are not part of your set. If you show something's not a context-free language with the pumping lemma, you might be able to show that something else is not context-free because these operations are closed for context-free languages. So let's quickly review what's closed for context-free languages, what's closed for deterministic context-free languages. I gave you this chart. You can kind of glance at it while we go through this. I won't go through any complicated proofs now. Your brains have done a lot of detail. We'll stick with the big picture right here, and we'll talk a little bit about closure and decision algorithms. I'll do this in more detail. We're going to have one more lecture about context-free languages before we go to the next jump up. And we're just going to intro today and talk about a neat problem before we quit. So let's write these down. CFL.
Explain the chart with DU and T.
Maybe. D means decidable, U means undecidable, and T means trivial. T means true. It means it's for sure decidable. It's just the answer is always yes.
How is that different than decidable?
It's not. You could have just written D, but if you wrote D, somebody would think that you really need a clever algorithm. The algorithm for the T's are print line yes.
Oh, okay.
Okay, so they're trivially decidable. It's like, here's a question about finite state machines that is trivial. I give you a regular expression, and I ask you, is the language represented by this regular expression regular? And you say, well, yes, it is, and wonder why I would ask you that. That's a trivial problem. So is the complement, I give you a language that's described by a finite state machine. I ask you, is its complement also regular? What do you say? You say yes. That's a trivial decision algorithm. If I give you a context-free grammar, and I ask you, is the complement of the language generated by this grammar also context-free? That's a hard question. It might be and it might not be. And let's see if we can find that here. Is the complement of the language also a language of the same type? Regular sets? Trivial. Deterministic context-free languages? Trivial. Context-free languages? Undecidable.
What used to be under that you scribbled out there?
Yeah. I don't know.
I think the other one goes from unknown to trivial.
Yeah, there's a little star. This was solved last year, 1990.
So we didn't have to bother with the one in the middle. So we just went right to trivial.
That's right. It turns out that the complement of any context-sensitive language is also a context-sensitive language. They're closed under complement.
Does that mean Turing machine?
No, it's a little less than a Turing machine.
Okay.
It's algorithms that run in order n space.
Oh, right.
Well, so let's review some of these closure properties and decision algorithms. First, these closure properties. CFLs, are they closed under union? Yes or no?
Yes.
Why? Who can prove that to me with an explanation? Don't say because it says so on the sheet. I cross things out on the sheet, right? So how can you trust it? Why are context-free languages closed under union? What?
Union isn't on the sheet anyways.
I put them up on top.
Yeah.
See the little things I wrote in? It wasn't on the sheet. I don't know why, but why do you think they're closed under union? Convince me that if you give me two context-free languages, that I can union them together and get another context-free language. Here's the proof. All right. I guess this proof means you make two E moves from a new start state to the start states of the two machines you're given. All right. I like to do this proof with grammars because it seems more natural with grammars. You don't have to talk about E moves. If somebody gives me two grammars, start symbol S, start symbol T, then I just make a new start symbol, M, and M goes to S, M goes to T, and that generates the union. There's a lot of ways to prove it. It's definitely closed under union. All right, it's not closed under complement. It's not closed under intersection. It is closed under reversal. How do you show the context-free languages are closed under reversal? In this case, there is really one easy way to do it and one hard way to do it. If you look at the machine, you're really in trouble. Reversing these push-down machines are really hard. You got to reverse the stack operations and turn the arrows around. I remember when we reversed them, sometimes non-determinism occurs. It was a big mess, even for finite state machines. To do it with push-down machines, it's really a mess. So how do you do it with grammars? You can just take the right sides of all the productions and turn them around. Then anything that you used to generate before generates the same way, except it ends up reversed. It generates exactly the reverse of the original language. Just take all the productions and turn them around. Look at them through the other side of the blackboard. So context-free languages are closed under reversal. There's a few of these other sets like min and max and cycle that I talked about for finite state machines. Regular sets, they're closed under all of them. Context-free languages happen to be closed under cycle, but not under min and max. Deterministic context-free languages are closed under min and max. I won't talk about the details there. They're not so obvious, but they're not impossibly hard either. They're things to think about. More importantly, deterministic context-free languages are closed under complement, but not under union. More or less, the proof that deterministic context-free languages are closed under complement is that toggle final, non-final states proof. There's some technicalities, but it's more or less that simple proof. You can't toggle non-deterministic machines and get the complement. It doesn't work. But you can toggle deterministic machines and get the complement. How come deterministic context-free languages are not closed under union? It's because if you do that same e-move trick, you get non-determinism. And if you do the grammar trick, where the new start symbol goes to S and to T, that turns out to be a grammar that's not of an LRK form. So there's no way to obviously union deterministic context-free languages together, and in fact, they're not closed under union. In fact, here are two deterministic context-free languages. And if I union them together, I get a provably non-deterministic context-free language. There's no deterministic language that gets their union. So definitely not closed under union. Context-free languages are closed under concatenation. How do you prove that?
You move from the except of the first one to
Okay, you can do that e-move from the except of 1 to the... But doesn't that make it non-deterministic? I guess it's okay. It's non-deterministic. What about the grammars? Can you do it with a grammar? You have two start symbols for two grammars, S and T. Make a new start symbol that goes to S, T. So you can do it with grammars too. What about star? Is it closed under star?
Yes.
How? How do you show that it's closed under star? Because it says so. If I have a grammar, S, context-free grammar, generates a lot of stuff. How do I make a new grammar that generates any repetition of any string here? I'm not sure that would give me everything.
A new start state that goes to S or SS.
So a new start state, S new, that goes to...
S or...
What about this? What does this do? Or epsilon. What does this do? S new goes to S, S new. It's a Dr. Seuss thing. What's new? SNU goes to SS new. You go ahead and do this once, and you get SS S new. You do it again, you get SSS S new. Sooner or later, S new is going to disappear. So this gives you as many copies of S as you want. And that's it. That's the proof.
You could just have S go to SS.
Yeah, right. I think that's okay too. Yes. What about DCFLs? Are they closed under concatenation or star? It's not at all obvious. Because for one thing, you can't do these tricks in grammars and expect them to stay LRK. And you can't go ahead and make e-moves from final states to new states.
Could you just clarify for grammars what DCFLs are?
I can't. It would take me an hour and a half.
Okay. Because it's clear from the machine point of perspective, but from the grammars...
It is just not clear. It is It's an hour and a half. An hour and a half of lots of details, examples, and not obvious. There is no simple way to look at a grammar and say, hey, that's an LRK grammar. There's a complicated way to look at it. Compute what's called the first sets. Compute the follow sets. Compute the list of legal items. It's a big procedure. And even when you do it many, many times, you have to really go through the details before you know the answer. Even when you're good at it and intuitive at it, it's rare to be able to glance and still have the right idea in advance without going through the details. So I keep just saying LRK, and it would be nice if I could give you the intuition, but we need to spend 2 or 3 recitations on it. And hopefully we will. Okay, so this tells you a little bit about closure problems. I'll get back to closure and decision algorithms in more detail tomorrow. I want to leave you with this one puzzle. And it's not just an arbitrary puzzle. It relates to undecidability. It's called the post-correspondence problem. You can read a lot about the post-correspondence problem in your text, in any of these texts that we have on reserve. And also, somebody was reading Gödel Usher Bach, I forget who, this month. That's a Pulitzer Prize winning, I don't know what you want to call it, book. It's not a novel. It's just a weird book by, who's it by? By Hofstadter, who's at Indiana, I think. And he did some AI and some theory. And anyway, he wrote this book from ideas in his early graduate days. And it's kind of a weaving of music, art, and theory of computation all into one, where the music is the fugues of Johann Sebastian Bach, and the art is mostly M.C. Escher, and the theory is mostly Kurt Gödel and all these things you're learning this month. In it, he talks about the post-correspondence problem in his very clever, interesting way. But let me just tell you what it is, because it's a cool problem. Somebody gives you 2 sets of strings. This is number 1, number 2, number 3. This is list A, list B. So there's 3 pairs here. In the general problem, somebody gives you any number of pairs. Here there's just 3 in the list. And the question is, can I make a sequence of these numbers? For example, 1, 1, 3, 2, 2, 1. Can I make a sequence of these numbers so that when I go ahead and concatenate all the strings from each list, A, B, in that order of that sequence, that I get the 2 strings to be the same? Let's try it in this example. 1, 1 means, let's do the A part. A would be 1, 0, 1, 0. 3 would be 1, 1, 0, 1, 1, 0. 2 2s would be 1, 1, 1, 1, 1, 1. And then another 1 would be 1, 0. And then for B, it would be 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 2 2, 0, 1, 0, 1, and then another 1, 1, 0, 1, 1, 0. Okay, so that's that particular sequence I came up with, generates this for A and for B. And the question is, are they the same? They're not the same. The question is there a sequence that makes them the same? The sequence you come up with can be arbitrarily long. Or can you look at it and convince me that there's no sequence that will ever work? Does everyone understand the problem or the puzzle? So given a set of pairs, can you do it or can't you? Can you come up with a sequence that makes these 2 strings even out, or can't you? In his book, he comes up with a very nice example, and I forget who's having the conversation in the example, the tortoise and the Achilles and who knows who. But the turtle and the Greek hero are having a conversation about this problem, and one of them convinces the other that there's no way to do it for the particular set of strings that they talk about. And it's a very clever argument. Something about the parity of the strings, that any sequence here has an odd number of 1s and any sequence here has an even number of 1s, and there's no way to do it, and therefore the answer is no. And Achilles is impressed and says, let's look at another example. and they look at the other example and they play and play and play and play and play and can't figure out a match and also can't figure out any way to convince themselves that the answer is no. So it's interesting. This is a puzzle where if I give you certain strings, you might come up with a clever argument to explain why the answer is no. If the answer is yes, you can certainly write a computer program and go about your career and check it every few years and see if it spit out an answer that works, right? Because you can just generate the sequence of these numbers in order of length, you know, all the sequences of length 1, all the sequences of length 2, all the sequences of length 3, all the sequences of length 4. Try them one at a time, and sooner or later, a few centuries down the line, if there's an answer, it will spit out, and it will say, here it is, there's the answer. So you can definitely write a machine that tells you yes when the answer is yes. The question is, can you say the answer no when the answer is no? Occasionally you can if you're a human being and you're looking at a particular case and you come up with a particular idea. But to try to formalize that creativity in a mechanical way that will be able to look at any set of pairs and tell you yes or no in a logical kind of an argument turns out to be impossible. This is what's called an undecidable problem. You can answer yes if the answer is yes, but there's no way to write a program to guarantee to get the answer yes or no correctly. It's one of the highest level first undecidable problems. First you start with diagonalization, and then this comes out of it. And out of this, the reason I brought this up, and we're going to actually prove a lot of things from this problem. If this is undecidable, then so are all the important things you want to know about grammars. And that I can prove to you. All the interesting things that you'd like to do, if you could do them, it would solve this problem that everybody knows is impossible. That means all those interesting things that we really want to do about context-free grammars are impossible to do. They're all undecidable. And that way of connecting this to those problems is called a reduction. You've seen it before in algorithms in polynomial world. Now it's in the undecidable world. I'm going to reduce this problem to all these other problems about grammars and show you that those problems are hard too, because this problem's hard.